Okay, so this is a video on the second part of chapter 7, which is the progressive waves. The first part was on simple harmonic motion. Now the second part we're on progressive waves. Now what's the difference? The difference being, for simple harmonic motion, you move through space a little bit with time, but you don't really move through the space any higher than the amplitude. In other words, your displacement, sorry, your displacement for SHM displacement is limited to the amplitudes. Okay, now for progressive waves in general, you can have it to move indefinitely depending on the boundary condition given. So progressive wave is simply, right, it is simply a wave that travels continuously in the medium. Okay, and it doesn't change, it generally does not change its amplitude, because if it changes its amplitude, then it will die off. Then you have a problem. But for now, we're focusing on a wave that doesn't change. So now you don't only have as a function of time, but you also have it as a function of space, right? The displacement depends on where it is. Okay, and in general, we can use the same sort of trigonometric functions to describe a wave, a progressive wave, and we can make a simple assumption for its form to be kx plus and minus omega t. Now you still have the omega t, but now you have kx, just to say that it oscillates in space as well. Okay, now what does this k stand for? This k stands for wave number. Okay, and the key feature for this is actually, if you were to draw a graph of y against t and a y against x, okay, now we've seen in simple harmonic motion where if you have sort of something like that, you can take point to point, right, of one wavelength. That is just one wavelength. Okay, so if you are at this point, that means you have watched the first part of chapter 7, which is simple harmonic motion, whereas this video is going to be on progressive waves, the second part of oscillations and wave, chapter 7. Okay, so the main difference is that for simple harmonic motion, you just have sort of, for example, you have a pendulum goes back and forth, right? It doesn't really move in space. It does move in space, but in a limited boundary, right? But for progressive wave, one of this distinct feature is that it propagates through the medium. It will generally propagate away from the source of a progressive wave. Okay, so for example, if you were to just dip a stone or dip your finger into a bath of water and then just oscillate your finger is doing a simple harmonic motion, but the waves that comes from it, the oscillation of the water molecules, is what we call progressive waves. Okay, generally it will move outwards from the source of oscillation. Okay, so now we have sort of, say you put your finger into water here, and then you start to have waves coming out from it, and it generally will move away from the source. So wave functions, now it is not enough for us to just have y as a function of t, right? But it's also important for us to have y as a function of x, which is the general space that it's progressing in or propagating in. So a general approach that one can do would be to use the same description that we use in simple harmonic motion, which is a sine omega t, but then we change it with plus and minus kx. So now we have considered its propagation in space. Okay, so how do I make sense of this? Well, let me just refresh your memory. If I were to draw y against t, and then I draw a wave, right? I can say that the point from here to here, that is what we call the period, and the period is equal to 1 over f, and omega is equal to 2 pi f. So 1 over f would be just 2 pi over omega. So t equals to 2 pi over omega. Now, conversely, what I can do is well, not conversely, but what I can do is I can have a different wave, but rather than plotting it y against t, I will plot it y against x. Then I can draw the same thing again. This is my wave. Sorry, that looks like it's getting smaller. There we go. Okay, so now instead of having t, what I have here is what we call wavelength. It's the length measured, right? You can measure that length. Okay, and then that wavelength will be related to your wave number. So k here is actually your wave number. It is simply 2 pi over lambda. Okay, so what this means is that it has the units of per meter. So basically it means that how many wavelengths do you have per meter. Okay, that's what it means. All right, moving on. Now, knowing these two, let me just remind you that period has units of seconds. Has units of seconds. Now we have a wave. We want to know how fast this is moving, right? The propagation velocity. So what we call the propagation velocity, v. Quite simply, what you can do is look at the units and see what works, right? And here what we can see is actually f lambda would work because it's s-1 and meters, right? So it's just meters per second, right? So here will be meters per second. Now, of course, my frequency is just the omega, right? 2 pi over omega, omega over 2 pi. So this is going to be, if I want to express it in omega, I'll have omega over 2 pi, and then lambda is just the inverse, which is 2 pi over lambda, 2 pi over k, which is your wave number, k. And here we get the new equation as well. So I have v equals to f lambda, that is true, but it is also equal to omega over k, right? Good. Now, some of you might have realized that in my equation for progressive waves, here, a sine kx plus minus omega t. Now, some of you might have realized I use plus minus because that plus and minus will determine if wave is moving in positive x direction or negative x. And there's a simple proof of this, which is if I were to say that kx minus omega t is equals to 0, right? Then I can have kx equals to omega t, and then I rearrange this x over t, which is just the velocity, which is going to be equal to omega over k, right? And this is going to be 0, so that means that it is moving in the positive x direction. Whereas conversely, if I have kx plus omega t equals to 0, then I will have kx equals to negative omega t. Then my x over t, which is equal to my v, is going to be equal to negative omega over k, which is less than 0. That means that my wave is moving in the negative x direction. Okay. All right. So now we have a problem because there's actually two types of velocity. You have the velocity of propagation. So velocity of propagation, which is v equals to f lambda equals to omega over k. But you also have the velocity, sorry, the vibrational velocity of particles. So the vibrational velocity will depend on the source. So for example, if I may use the example again, which is you put your finger into a cup of water, right? And then you vibrate your finger. Now, what you have is going to be, here's my peak, here's my throw, here's my peak again. You have a wave that is moving away from the source with some velocity. This is what we call the velocity of propagation. But how much or how fast you move your finger in and out to create those waves is what we call the vibrational velocity. All right, so this vibrational velocity, I'm just going to put vv, is simply going to be the first derivative, the first time derivative of my yxt. Okay, this can be quite easy to derive, which means it's just going to be as a function of t omega a sine kx plus and minus omega t. That is going to be my vibrational velocity. Okay. Okay, so in the next part of this video, I'm going to talk about standing waves. Okay, so I'll see you then. Okay, we have reached the second part of this video, and I am going to talk about interference. Let's talk about interference first. Interferences. Now, interference is very simple to understand. Let's say I have, let's say in space, I have a wave, I have a peak, a throw, and then I have a second wave, which is also a peak and a throw, let's say something like that, and they meet, right? When they interfere, what they're going to be, what they're going to form, right? They're going to overlap with each other. Let's say the peak meets the peak, right? What I'm going to have is just a bigger peak, right? It's just going to be a bigger peak. But it's a very important but here. If I have a peak, oh sorry, wrong color. If I have a peak and I have a throw like that, I will get nothing because they cancel out each other. Okay, so this is basically just saying that if I have 1 plus 1, I will get 2. If I have 1 plus minus 1, I will get 0. That's what so the first case is what we call constructive, and the second part is what we call destructive. Okay, now knowing that, then what we can talk about is what we call stationary waves or standing waves. Okay, so standing waves, they do not propagate and they do not transfer energy, right? It is merely produced by the superposition of two progressive waves. Superposition simply means interference. Okay, so another name for this is superposition. Okay, one of the things that we need to show is actually this idea of superposition. So if I have a standing wave, let's call that y1. Sorry, if I have a progressive wave, let's call that y1, and I have a sine omega t plus and minus kx, and then I have one that is moving in the opposite direction, so let's give this a negative. Now I have another one that is moving in the opposite direction but has the same amplitude, so omega t plus kx. Okay, the principle of superposition simply means that my total or my resultant wave is simply going to be y1 plus y2. Okay, so how do I add them? Well, what we do know is that if I have two sine functions, sorry, if I have two sine functions, I have sine a plus or minus b, I can expand that into sine a cos b, then plus and minus cos a sine b. So now what we can do is I'm going to express both of these equations, y1 and y2, into this broken down formation. So I'll have a, then sine omega t cos negative kx, and I'll have plus and minus, sorry, I have minus I have cos kx omega t. Okay, and then I have minus cos omega t sine kx. Okay, and then plus, so this is y1, and then y2 be a, again the same thing. Difference is cos kx. Difference is here I'm going to have a plus, then cos omega t sine kx. Okay, there we go. Now we have a we have two equations that we need to add, right? But what you might realize is that these two are exactly equal except for their sign, so they can actually cancel out. Okay, so a plus a is just 2a, right? Then I have sine omega t cos kx. That's what I'll have. So my resultant wave will follow this wave function, okay, wave equation. Okay, so that's all for standing waves. In fact, if you want a visual representation, let's say I have one looking like that, then I have another wave, so let's say this wave is moving to the right, then I have another wave moving to the left. When they meet and they form a standing wave which doesn't move, right, which doesn't move, I can have it looking and forming something like this. Okay, it's just going to oscillate up and down. It's just going to oscillate up and down. That's all it's going to do. That's a standing wave, and it oscillates up and down with amplitudes of 2a. Say this is a. Okay, so in the next part we're going to be looking at case studies for these standing waves. Okay, so case studies for standing waves. Okay, so I'm going to go through three different cases, but before we do that, we should apply, or at least we should name profiles of a wave. So where it meets the axis, so where it meets the axis, here, 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 and here, is what we call nodes. And then where it is furthest from the axis, here, 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 and here, are what we call antinodes. From here on, I'm going to label this as an. I'm going to label this as n. Okay. For the first part, for the first case, we want to look at a stretched string. Stretched string. Okay. And in stretched strings, waves can form, right? And they can form when there's tension, and it depends on, and how fast that wave travels in the string depends on the mass density itself. So the relationship is actually my velocity of the wave on the string, okay, string, is simply going to be the square root of t over mu, where my mu is actually my mass of the string over the length of the string. This is what we call the mass density. Now, once I pluck the string, I can have waves progressing. Okay. Now the question is, what frequencies can I expect from the plucking or from the waves of this string? Now the first simplest case, so case one, the first simplest example that I can think of is if I have the two ends of a string, then I can have a wave which looks like that, a standing wave that looks like that. Okay, now if you see, it touches the ends at 2 points, right? This is what we call nodes. Again, these are called nodes, and this forms half a wavelength. So the length of the string, is actually equal to half a wavelength. Okay, half a wavelength. What that also means is that one wavelength is actually 2L. Now my velocity is depends on my wavelength by v equals to f lambda, and my lambda here is simply 2L. Okay, so my frequency is actually v over 2L. Okay, this is what we call the fundamental tone, or fundamental tone, or this is what we call the first harmonic. Another name for it is first harmonic. Okay. This is the lowest wavelength that can form on a string wave. Okay, we'll look at the second harmonic now. So let's call this the second harmonic, which is also called the first overtone. Over being it's over the fundamental. Okay, if I have again the ends of the strings here, then I can form a wavelength that looks a standing wave that looks like that, right? That now what we have here is my length is equal to my lambda. Okay, now the condition for the string, again, I would like to remind you, is that the ends must be at nodes. Okay, so my length is my lambda. That means my v equals to f lambda is actually also equals to fl. Okay, which means my frequency for my second harmonic, first overtone, so here I have my fundamental, and here I have my first overtone, will be v over l. Okay, that's perfectly fine to understand. Now we move on to our third harmonic, which is the second overtone. So third harmonic, second overtone, second overtone. Again, I can have the ends of the string, right? Then I can draw out what I know the standing wave on the string will form. It will look like that. Here, what I'll have is that my length is going to be, how many lambda is this? 1.5. So 1.5 is 3/2 lambda. Okay. So I have half a lambda, I have 1 lambda, and I have 1.5 of lambda, 3 halves of lambda. Okay, again, I can do the same procedure as before. V equals to f lambda. Here I have f times 2/3 lambda, sorry, no longer lambda, 2/3L, 2/3L, which means my frequency is going to be equal to 3/2 V/L. Okay, so to summarize, for string, when I have my fundamental, I had, let's see, V/2L. When I had my first overtone, I had V/L. And then when I had the third, the second overtone, I will have 2 equals to 3V/2L. Okay, now notice that there's 2L at the bottom for the fundamental and the second overtone. We might want to do that as well. I'll put it here. Okay, so 2/2, that's fine, that just cancels out. But if I just add another one here, you can start to see a pattern where if I have Fi, the top one will just be I plus 1, V/2L. And these form the possible frequencies, okay, for a stretch string. Okay, another way of writing this is actually my F is equal to NV/2L, with the condition that my N, right, is equal to 0. Sorry, not 0. It doesn't start with 0. It starts with 1. Well, it can start with 0, which means you don't have a wave. But it starts from 1, 2, 3, and so on and so forth. Okay. Okay. Now, we have done for stretch string. That's case number 1. Case number 2 will be an open tube. So an air column in an open tube. Imagine just an air column and then the sound wave that forms within it. Okay. Now, unlike the string where the ends must be nodes, here the ends must be antinodes. So antinodes. So the first possible frequency will look something like that. Okay, now where did I do this? How did I do this? Well, what I did was I have a string, I have a wave, and then all I did was cut here and cut here. That's how it looks like in an air column. Okay, so this is the most fundamental. So this is the fundamental. Okay, this is the fundamental, and this is actually, so my length, the length of the column is actually half a wavelength. That means my wavelength is 2L. Again, my V equals to F lambda, which means it's F times 2L. And again, I have F equals to V/2L. Okay. My v here refers to the speed of sound. Okay. So my fundamental node will be v over 2l. Rest assured, you can do the same thing again for the first overtone. So first overtone, right? So instead of cutting it A and B, I can continue on my wavelength like that. Sorry, my waves like that. Instead of cutting A and B, I can cut A and C here. So what that means is that I can have a wave that looks something like that. Okay, looks a bit more like a DNA, but that's fine. Here I have my length to be how many? 1, 2, that's half a wavelength. 3, 4, that's a full wavelength. So then I have L equals to lambda. That means my V is equals to FL, meaning my F is equals to V over L, so which is 2 over 2. Again, rest assured that my second overtone will have the successive, which is F equals to 3V over 2L. Okay, 1, 2, and 3. So what that means is that for an open tube, I have similar functions, similar equations with the stretch string case, which means generally my frequencies will be NV over 2L, where my N is equal to 1, 2, 3, and so on and so forth. Now the last part would be a closed-ended tube. So 3 closed-ended tube. Okay, now for closed-ended tube, it should look something like this. I tilt it to make it easier. But the condition that you have is going to be node and antinode. So if I were to draw a graph like that, okay, I can start from A here, but I have to cut it either B or C, the simplest of which will be just A and B. So let's do that. That will form the fundamental frequency. Okay, and here you can see that for the fundamental frequency, right, its length is actually 1/4 of the lambda. Then I have lambda equals to 4L. Then I have V equals to F for L, and that means that I have fundamental frequency equals to V over 4L. That is the fundamental. Okay, so now what we want to do is the first overtone. So first overtone, meaning I take A to C. Okay, so if I have a closed-ended tube, I can have it going up and come back down, but never closes. It should look something like that. So A and C. Okay, as you can see here, this is not 2/4, or it is actually 3/4. So that means my length, the length of the column, is actually 3 over 4 lambda. What that means is that lambda equals to 4 over 3 L, and my velocity is actually F and then 4 over 3 L. Means my first overtone actually happens 3 over 4 V over L. If you continue on with this pattern, right, you will find that you actually have an equation that looks something like this. You have a general equation for closed tube. I will have F equals to NV over 4L, where N is equal to either 1, 3, 5, 7, and so on and so forth. These are odd numbers. Odd numbers. Okay? These are all odd numbers. So this is going to be your general equation. Of course, I can make it relatively simpler, but you can also change the values. You can change such that I can have f equals to 2n plus 1 v over 4l. So let's just check that. I can have n equals 2 starting from probably 0. Yeah, 0, 1, 2, 3 if you want it to be whole numbers, like that. Then if I check that, 0, 2 times 0 is just 0 plus 1. So the first one would be v over 4l. The second one would be 2 plus 1. So that is not right. It should be 2n minus 1. 2n minus 1. So then I have, okay, 2 times 1 is 2. 2 times 0 is nothing. It's negative. So I'll get rid of the 0. Okay. All right. So 2 times 2 is 4. 4 minus 1 is 3. 3 over 4. That is the first overtone, which coincides with this position. First overtone. First overtone. And then 3. 2 times 3 is 6. 6 minus 1 is 5. 5 over 4. That is the second overtone. But there's a benefit of doing this, because it tells you the harmonics that can happen is the first, third, fifth, and seventh. No even numbered harmonics. With that said, I think it best to be reminded that harmonics is simply the integer multiples of the fundamental. Okay, so if I say the second harmonic, I mean it's going to be twice the frequency. Here in the open tube, sorry, in the closed tube, you do not have even numbers. You do not have frequencies that is double the fundamental of or quadruple. That doesn't happen. Okay. Okay, so that is all from me. Thank you very much. I'll see you in the next video.